Welcome to this explainer. Today, we're going to do something really special. We're taking one of the most notoriously intimidating concepts in physics, a concept that is heavily layered in complex calculus and massive mathematical equations, and we're going to turn it into a highly visual, totally intuitive journey. If you've ever looked at a physics textbook and felt completely lost in a sea of Greek letters and integral signs, you are absolutely in the right place. We are going to strip all of that back and build up your understanding using purely visual concepts. Get ready to see the invisible.
We're starting our journey with a brilliant 19th century mathematical genius, Carl Friedrich Gauss, whose work fundamentally reshaped our entire understanding of the universe. What's absolutely mind-blowing about Gauss is that he created this profoundly elegant rule governing the fundamental forces of our modern electrical world long before we even had things like light bulbs or computers. He wasn't just doing math for math's sake, he was building a conceptual framework to understand the very fabric of nature. And today, we're going to look through his eyes to see exactly how he pulled it off.
But before we can dive into his famous law, we've got to start with a really fundamental question. And it's a tricky one. How do we actually measure something we can't see? I mean, we know electricity's there, right? We feel that sudden static shock from a doorknob, we see the sheer power of lightning, and we know these invisible forces are acting all around us. But how do you quantify a totally invisible force field that's just spreading out into empty space? Well, that was the exact puzzle Gauss set out to solve.
Section 1. Visualizing the electric field.
To really understand this, we have to give this invisible force a shape in our minds before we can even attempt to measure it. So think of a central positive charge, kind of like a 3D water sprinkler. Just imagine it suspended in midair, constantly spraying water outwards in every single direction into the space around it. In physics, instead of water, we have these continuous electric field lines pointing away from the charge. They perfectly represent the direction and that endless outward push a positive charge exerts on the universe. It literally never stops flowing.
And this visualization gives us our absolutely crucial baseline concept, the electric field, which we simply denote with the letter E. This is that invisible region of influence radiating outward from a given charge. I really want to emphasize this point. Just by picturing that 3D sprinkler spraying outward, you are already grasping the deep physics here. Before we've introduced a single drop of math, you now know exactly what an electric field looks like in your mind's eye.
Section 2. Casting the Gaussian surface.
Okay, so knowing the spray is out there is one thing, but actually calculating how much is spraying, that's another entirely. To measure that outward flow, Gauss realized we need to trap it, so we basically cast an arbitrary, completely imaginary boundary entirely around the charge. We call this a Gaussian surface. Think of it like a perfectly porous, spherical net designed to catch every single line of flow coming from that central charge. And honestly, it doesn't matter at all if you imagine this boundary as a blue sphere or a green sphere, the concept is identical. We are just wrapping the charge in a mathematical bubble to see how much of that field pierces through.
Section 3. Calculating the electric flux. Now that our net is securely cast around the charge, we've got to translate that visual net into the language of physics. And what's really cool here is how simple these mathematical symbols actually are when you connect them back to what we just visualized. We've got a little cast of characters. There's phi, which just means the total electric flux or the total amount of our spray passing through the net. Then we have E, our electric field. Qn is just the total charge trapped perfectly inside our net, and epsilon naught, that's simply a constant number representing the physical properties of the air or vacuum around the charge. But here is the most crucial part, so don't let this trip you up. Whether a textbook calls a tiny microscopic patch of area on our net dA or ds, it is the exact same thing. Don't let the different letters confuse you. They both literally just mean a tiny piece of the net.
By looking at the full mathematical derivation for a spherical charge, we can begin to see how all those physical variables actually interact. Now, I know looking at an integral sign with a circle through it can trigger some immediate math anxiety, but stay with me here. That symbol simply means, hey, let's add up all the spray passing through every tiny patch of our totally closed spherical net. It's nothing more than a summation tool. It's just adding up the electric field E multiplied by every tiny patch of area.
We can break this whole thing down into logical steps without any panic whatsoever. Step 1, we set up the total flux integral. We're basically just saying, let's measure the total flow. Step 2 is where the magic of the sphere really comes in. Because our net is a perfect sphere, the outward spray, that electric field E, is exactly the same strength everywhere on the surface. Because it's constant, we can just yank it right out of the scary integral. Step 3, now we just need the total surface area of our spherical net, which is basic geometry, right? 4 times pi times the radius squared. And finally, step 4, we just reorganize to solve for E. See? The terrifying calculus just melted away into simple algebra, all because we chose a beautifully symmetrical net.
Section 4. Unlocking Gauss's law.
So how do all of these conceptual steps, the visual sprinkler, the imaginary net, and those physical variables, finally unify into one master equation that changed physics forever? Well, here it is, the grand finale. Instead of seeing this as intimidating math, we can actually read this master equation beautifully, left to right, like a simple, elegant sentence. It says, phi, the total electric flux passing through our fully closed net, is exactly equal to the total charge enclosed inside that net, divided by a fundamental constant of nature, epsilon naught. That is Gauss's law. The amount of field piercing out is directly proportional to the amount of charge trapped within. It absolutely doesn't matter how big you draw the net or what color it is. The total flow caught by the net always perfectly reveals the hidden source inside.
As we wrap up this explainer, we're left with an incredibly exciting mystery to ponder. We just saw how easily the math collapses when we use a perfectly symmetrical, spherical net to trap the field of a simple, perfectly round point charge. But the universe is rarely that neat, is it? So it leaves us wondering, if this invisible net works so perfectly for a simple sphere, how in the world do we adapt it to measure the bizarre, chaotic, and completely asymmetrical charge distributions found throughout the complex electronics and strange structures of our universe? Think about that. Until next time. Keep visualizing and keep learning.